Now we will discuss about Earth's magnetism. Earth as a magnet. When we have a magnet and when we allow this magnet in space, which has got a magnetic field, then a torque will act on it. We discussed it already in the previous topic. In figure, you can see a uniform magnetic field. If we are considering a small magnet in this magnetic field, then in figure you can see two forces will act on this magnet in opposite directions. And these two forces make a torque, and this torque rotate the magnet. And finally, the magnet will align in the direction of the field that you can see in the next figure. In the second figure, you can see the north and south poles of the magnet. Now, in this condition, the torque becomes zero, and this is the equilibrium condition. Now, the question is when this happens? When there is the presence of magnetic field. The same thing you will observe in the case of compass needle also. In figure, you can see a compass needle in a magnetic field. As in the previous case, here also on the compass needle, a torque will act. As a result of this, finally, the compass needle will align in the direction of magnetic field. Now we will see the examples for the presence of magnetic field at any location. If you suspend a bar magnet at any point, it will go to a particular direction of magnetic field. If you displace it angularly, again it will come back to the same situation. This shows the presence of magnetic field. If I have a magnet and if I suspend it, it will align in a particular direction. If I go to the next room, then also the same thing will repeat. That means I am getting a magnetic field everywhere. Now the question is, which magnetic field is present everywhere? The source of this magnetic field is Earth itself, or we can say the Earth behaves like a magnet. Now we will study Earth's magnetic field in detail. Magnetic field is a vector quantity, so we should check both magnitude and direction. The magnitude of Earth's magnetic field is in the order of 10 power minus 5 Tesla. If we check a compass needle, we can see it rotates freely and it will always stay in the direction of magnetic field. If we are trying to trace the direction of Earth's magnetic field with a compass needle, in figure you can see the needle always points to the north of the Earth. So, a magnetic needle is a very good tool to find the north direction. Now we will discuss the cause of Earth's magnetic field. First, it was thought that the magnetic field of the Earth was arising from a bar magnet placed approximately along the axis of rotation of the Earth. But this assumption is not correct. In figure, you can see the interior of the Earth. Here, the difference in temperature, pressure and composition within the outer core of the Earth produces convection currents in the molten metal. This flow of liquid iron generates electric currents, and we know when there is electric current in the surrounding region, one magnetic field will be created. So, the magnetic field of the Earth is due to the electric currents produced by the motion of metallic fluids in the outer core of the Earth, and this effect is known as Dynamo Effect. We can use a compass needle for tracing the magnetic field lines of the Earth. In figure, you can see the needle always points towards the north. But here, the important thing, the north pole traced by the compass needle is not the geographic north pole. That is, there is a difference between the north pole traced by the compass needle and the geographic north pole of the earth. In the previous slide, we already checked that the north pole traced by the compass needle and the geographic north both are not at the same point. In fact, the Earth's magnetic field is like that of a bar magnet whose axis is inclined by approximately 11.3 degree with respect to the axis of rotation of the Earth. In figure, you can see the angle 11.3 degree. For explaining the magnetism of Earth, we can assume a bar magnet inside the Earth. In figure, you can see a bar magnet with north and south poles inside the Earth. But here, the important point, the south pole of this bar magnet is towards the geographic north and the north pole of this bar magnet is towards geographic south. And the magnetic pole near the geographic north pole we are naming as north magnetic pole. The magnetic pole near the geographic south pole we can name it as south magnetic pole. Here, geographic axis of the earth is a straight line passing through the geographic poles of the earth. And the magnetic axis of the earth is an imaginary straight line passing through the magnetic north pole and south pole of the earth. Now we will check the terms once again. Here, NG is geographic north, SG is geographic south, NM is magnetic north and SM is magnetic south. And inside the earth we are assuming a bar magnet. S and N are the south and north pole of this bar magnet. Geographic axis is a straight line connecting NG and SG. Magnetic axis is a straight line connecting NM and SM. When we are checking the magnetic field lines of the earth, we can see the field lines are going into the earth at north pole and it is coming out from the south pole. But this part is confusing when we compare it to that of a bar magnet. If we are checking the field lines of a bar magnet, we can see the field lines are moving away from the north pole and it is coming towards the south pole. In fact, the north magnetic pole of the earth behaves like the south pole of the bar magnet inside the earth. Next is elements of earth's magnetism. The physical quantities which determine the intensity of earth's total magnetic field in magnitude and direction are called magnetic elements. There are three elements of Earth's magnetism: angle of declination, angle of dip, and the horizontal field strength of Earth's magnetic field. First, we will discuss angle of declination. In figure, you can see the two terms geographic meridian and magnetic meridian. Geographic meridian at a place is a vertical plane passing through the geographic north and south poles of the earth. Magnetic meridian is a vertical plane passing through the imaginary line joining the magnetic north and south poles of the earth. In figure, you can see there is an angle between geographic meridian and magnetic meridian. The angle between magnetic meridian and geographic meridian is called declination. In figure, you can see the compass needle is pointing towards the magnetic north. The angle between the true north and the magnetic north is declination. Next is angle of dip or inclination. In figure, you can see a compass needle. It points in the direction of total magnetic field of the earth. You can also see the horizontal line. The angle between total magnetic field of the earth and the horizontal is dip. At the magnetic equator, the magnetic needle is horizontal, therefore the dip will be 0. At the magnetic poles of the earth, the magnetic needle will be vertical, so the value of dip will be 90 degree. Next is horizontal field strength. The total magnetic field of the earth can be resolved into two rectangular components, one along the horizontal and the other one along the vertical. The component of the total magnetic field of the earth along the horizontal is called horizontal field strength, and the component along the vertical is called vertical field strength. In figure, you can see the total magnetic field of the earth BE. We can resolve BE into two components. Along the horizontal direction, it is BH, and along the vertical direction, it is BV. BH is the horizontal field strength. From figure, we can write BH is BE cos theta and BV is BE sin theta. Therefore, tan theta will be equal to BV by BH.